In the last few videos, we've explored what agentic AI is, how agents think, and how they remember. But there's a pattern emerging in the most powerful AI systems today. They're not using one agent. They're using many. Teams of agents, hierarchies of agents, networks of specialized agents working together on problems too complex for any single system to solve. Here's what's fascinating. When researchers put multiple agents together, something unexpected happens. Performance doesn't just add up, it multiplies. One study found that multi-agent systems outperform single agents by over 90% on complex reasoning tasks. Why? Because agents working together can do something a single agent can't: challenge each other, catch each other's mistakes, and combine different perspectives into better solutions. In this video, we're going to explore the world of multi-agent systems, why single agents hit limits, how teams of agents are architected, and why this might be the most important pattern in agentic AI today. Let's dive in. Let's start with a question. If one agent is powerful, why would we need more than one? The answer comes from a fundamental limitation. As tasks get more complex, single agents start to struggle. Not because they lack intelligence, but because they lack perspective. A single agent has one reasoning thread, one approach, one set of biases. When it makes a mistake early in its reasoning, that error compounds through every subsequent step. There's no one to say, "Wait, are you sure about that assumption?" There's another limitation: context windows. Even the most advanced agents can only hold so much information at once. When a task requires synthesizing information from dozens of sources, coordinating multiple subtasks, or maintaining state across long operations, a single agent's working memory becomes a bottleneck. It's like asking one person to simultaneously be the researcher, the analyst, the writer, the editor, and the project manager. Even brilliant individuals struggle when stretched across too many roles. Perhaps the deepest limitation is verification. How does an agent know if its answer is correct? It can check its own work, but it's using the same reasoning that produced the answer in the first place. This is like proofreading your own writing. You tend to see what you meant to write, not what you actually wrote. Single agents can engage in self-critique, which helps. But there's something fundamentally more powerful about having a separate entity with its own perspective evaluate your work. So, how do we organize multiple agents? There are two fundamental patterns: hierarchical and horizontal. In a hierarchical system, there's a lead agent that breaks down goals and delegates to specialist agents. Think of it like a manager coordinating a team. The lead agent decides what needs to be done, assigns tasks to the right specialists, and synthesizes their outputs into a final result. This pattern works well when tasks can be cleanly decomposed and there's a clear chain of command. The horizontal pattern is different. Here, agents are peers. They collaborate, debate, and reach consensus. No single agent is in charge. Instead, they share information, challenge each other's conclusions, and collectively converge on solutions. This pattern shines when problems require diverse perspectives, and when the right answer isn't obvious. It's messier than hierarchy, but it can produce more robust results because every conclusion has been stress-tested by multiple viewpoints. In practice, many systems use a hybrid approach. A lead agent provides overall coordination, but specialist agents have autonomy within their domains and can collaborate horizontally with each other. Think of it like a well-run company. There's leadership setting direction, but teams have the freedom to self-organize, and experts consult with each other directly. The key insight is that architecture should match the problem. Highly structured tasks benefit from hierarchy. Creative or ambiguous problems benefit from horizontal collaboration. There's one more architecture worth knowing: adversarial systems. Here, agents are intentionally set up to challenge each other. One agent proposes solutions, another agent tries to find flaws, a third agent judges the debate. This might seem inefficient, but it's remarkably effective for catching errors and hardening conclusions. The key insight from research is that agents debating each other reach better answers than agents working alone, even when the individual agents are equally capable. The magic is in the interaction, not just the intelligence. Multiple agents need to communicate, but how? The simplest approach is message passing. Agents send structured messages to each other, requests, responses, status updates. This is explicit and traceable. You can see exactly what information flowed between agents. But it requires designing the message formats and protocols up front. It's like email between team members, clear and documented, but requires coordination on how to structure the communication. Another approach is shared memory. Instead of passing messages directly, agents read and write to a common workspace. Think of it like a shared document that everyone can edit. One agent writes its findings. Another agent reads those findings and adds its analysis. A third agent reads both and synthesizes. This is more flexible than message passing and can handle complex, evolving information, but it requires careful management to avoid conflicts and ensure agents are reading the latest state. Coordination gets harder as you add agents. Who decides what to work on next? How do you prevent duplicate effort? How do you handle conflicts when agents disagree? These are classic problems from distributed systems, and multi-agent AI faces them all. The solutions borrow from decades of computer science: locks and semaphores to prevent conflicts, consensus protocols to resolve disagreements, task queues to coordinate work. Building reliable multi-agent systems means taking coordination seriously. Here's what makes coordination truly powerful: emergent behavior. When agents interact according to simple rules, complex behaviors can emerge that no single agent was programmed to produce. A group of simple agents, each following local rules, can collectively solve problems that would stump any individual agent. This is how ant colonies find optimal paths and how flocking birds navigate without central control. Multi-agent AI systems can exhibit similar emergence, where the whole becomes greater than the sum of its parts. Let's look at how multi-agent systems perform in practice. Researchers at various institutions have tested what happens when you add agents to reasoning tasks. The results are striking. On complex problem-solving benchmarks, multi-agent systems consistently outperform single agents. One comprehensive study found improvements of over 90% on challenging reasoning tasks. But here's the nuance. More agents isn't always better. There's a sweet spot, usually between 3 and 5 agents, where you get the benefits of diverse perspectives without the overhead of coordination. Consider software development. A single coding agent can write code, but a multi-agent system can do something more sophisticated. One agent writes the code. Another agent reviews it for bugs and security issues. A third agent writes tests. A fourth agent checks if the code meets the original requirements. Each agent brings a different perspective, and the final code has been examined from multiple angles. This mirrors how human development teams work, with different roles catching different types of issues. Research and analysis is another powerful application. Imagine investigating a complex question with multiple facets. A research agent gathers relevant sources. A fact-checking agent verifies claims. An analysis agent identifies patterns and insights. A synthesis agent combines everything into a coherent narrative. A critic agent challenges the conclusions and looks for gaps. Working together, these agents can produce research that's more thorough and more reliable than any single agent could achieve. One of the most impressive demonstrations is in mathematics and formal reasoning. When agents debate mathematical proofs, checking each other's logic step by step, They catch errors that individual agents miss. The back and forth forces each agent to justify its reasoning explicitly, making hidden assumptions visible. This adversarial verification has proven remarkably effective. Systems using agent debate have solved problems that stumped single agents, not through raw intelligence, but through the rigorous verification that comes from having to convince a skeptical peer. If you're thinking about multi-agent systems, here are the key principles. First, specialize your agents. Each agent should have a clear role and expertise. A generalist team of identical agents performs worse than a team where each agent brings something different. This is the principle of cognitive diversity. Different perspectives, different approaches, different potential errors. When agents are too similar, they make the same mistakes. When they're different, they catch each other's blind spots. Second, design the interaction carefully. How agents communicate matters as much as what they know. Should they share all information freely or selectively? Should one agent see another's reasoning process or just its conclusions? Should agents debate synchronously or work in parallel and compare results? These design choices significantly impact outcomes. There's no universal right answer. The interaction pattern should match the problem you're solving. Third, build in reflection. The most effective multi-agent systems don't just produce answers, they reflect on their process. Did the agents collaborate effectively? Were there communication breakdowns? Did one agent dominate inappropriately? Building in explicit reflection steps, where the system evaluates its own teamwork, leads to better outcomes over time. This meta-level reasoning, thinking about how you're thinking together, is what separates sophisticated multi-agent systems from simple agent combinations. If you're finding value in understanding how AI systems are evolving, make sure you're subscribed to this channel. We go deep on agentic AI, from single agents to multi-agent systems, and everything in between. If this video helped you understand how agents work together, hit that like button. It helps more people discover this content and join the conversation about agentic AI. And ring that notification bell so you don't miss the final video in this series, where we look at where agentic AI is headed. The future is closer than you think. Let's recap what we covered. Single agents hit limits because they lack perspective, run out of context, and can't truly verify their own work. Multi-agent systems solve this through architecture. Hierarchical teams with lead agents coordinating specialists, horizontal teams of peers debating as equals, or adversarial setups where agents challenge and strengthen each other's conclusions. Communication happens through message passing or shared memory, and coordination borrows from decades of distributed systems research. The results speak for themselves: 90% improvement on complex reasoning tasks, with a sweet spot of 3 to 5 agents. The key insight? The magic is in the interaction. So now you understand why the most powerful AI systems aren't single agents. They're teams, hierarchies of specialists, round tables of peers, adversaries who make each other stronger. The principle is simple but profound. Multiple perspectives, properly coordinated, produce better results than any individual, no matter how intelligent. We've covered a lot of ground in this series. What agentic AI is, how agents think, how they remember, and now how they work together. But there's one more question to answer. Where is all of this going? What does the future of agentic AI look like? That's the topic of our final video in this series. If you haven't already, subscribe to the channel and ring the notification bell so you don't miss it. Check out the other videos in this series if you're just joining us. And drop a like if this helped you understand multi-agent systems. I'll see you in the final video, where we look at where agentic AI is headed. The future is being built right now,